What could possibly make the most sophisticated artificial intelligence system ever pointed towards space suddenly flag something as impossible? The question haunts every data analyst who has witnessed the moment when machine learning algorithms encounter patterns they were never designed to recognize. Tonight we explore such a moment when the James Webb Space Telescope's neural networks identified something within the faint glow of a distant visitor that defied every known law of cosmic illumination. The discovery began not with human eyes peering through eyepieces, but with silicon minds processing millions of spectral measurements per second. Artificial intelligence systems aboard the Webb telescope scan each incoming photon for anomalies, comparing new observations against vast databases of known cosmic phenomena. These algorithms have catalogued the light signatures of dying stars, forming galaxies and planetary atmospheres across 13 billion years of cosmic history. Yet on this particular evening in late summer, something triggered an alert that had never appeared before. Hello dear listeners, and welcome to our journey through one of the most profound discoveries in human history. Today we explore the moment when artificial intelligence recognized artificial intelligence across the vast darkness of space. Before we continue deeper into this extraordinary detection, take a moment to settle in wherever you are listening, perhaps in bed, on a quiet evening walk, or during a peaceful moment of your day. If stories like this help you relax and discover new wonders, consider subscribing or liking this program. It helps more curious minds connect with these calming explorations. Now let your thoughts drift as we delve into the patterns that revealed we are not alone in developing technology. The Webb telescope's artificial intelligence operates through layers of pattern recognition that function much like human intuition, but with mathematical precision. Neural networks trained on cosmic data learn to distinguish between the random fluctuations of natural phenomena and the organized structures that suggest deliberate design. When starlight passes through interstellar dust, it creates predictable scattering patterns. When gas clouds collapse under gravity, they emit characteristic spectral lines. These natural processes leave signatures that follow physical laws, creating patterns that artificial intelligence can readily identify and categorize. But within the gentle radiance emanating from 3I/ATs, the algorithms detected something fundamentally different. The light contained geometric regularities that appeared nowhere in their training databases. Spectral emissions occurred at frequencies that matched no known atomic transitions. Most remarkably, these anomalous signals demonstrated temporal coherence. They pulsed in synchronized patterns that suggested coordination across vast distances. The initial alert triggered a cascade of automated analysis protocols. Machine learning systems began comparing the anomalous signals against every known natural phenomenon. They examined pulsar emissions, stellar magnetic field interactions, and the complex chemistry of interstellar molecular clouds. Each comparison strengthened the conclusion that these patterns originated from technological rather than natural sources. Pattern recognition algorithms excel at identifying structures that human perception might overlook. Where we see random noise, they detect hidden correlations. Where we perceive chaos, they recognize underlying order. The artificial intelligence systems monitoring 3I/ATLS identified geometric arrangements of light sources that form networks spanning hundreds of kilometers across the object's surface. These networks displayed properties characteristic of designed infrastructure, redundant pathways, hierarchical organization, and optimal distribution patterns that maximize coverage while minimizing energy expenditure. The spectral analysis revealed even more intriguing details. Natural light sources emit photons across broad wavelength ranges, creating the smooth spectral curves we observe from stars, gas clouds, and planetary atmospheres. But the anomalous emissions from 3I/ATAs showed sharp, narrow peaks at specific frequencies. These coherent emissions resembled laser light more than thermal radiation, suggesting technological origins involving stimulated emission and optical amplification. Machine learning systems trained to detect communication signals found additional evidence of intentional design. The temporal patterns within the light emissions contained nested frequencies, rapid oscillations embedded within slower rhythmic cycles. Such hierarchical timing structures appear in human-made communication systems, but remain absent from natural phenomena. The algorithms identified these as potential carrier waves, designed to transmit information across interstellar distances. The discovery process illuminated how artificial intelligence has transformed astronomical observation. Traditional astronomy relied on human researchers manually examining photographs and spectral data, a process that could take months or years to reveal significant patterns. Modern machine learning systems process observational data in real time, identifying anomalies within minutes of their detection. This computational capability allowed the Webb telescope to recognize the artificial nature of the emissions from 3I/A TLAS immediately, rather than after years of careful analysis. Yet the artificial intelligence systems also faced limitations in interpreting their discoveries. Neural networks excel at pattern recognition, but struggle with creative interpretation. They could identify that the light patterns were artificial, but not determine their specific purpose or origin. Human researchers became essential for understanding what these technological signatures might represent, whether they indicated propulsion systems, communication arrays, or entirely unknown applications of advanced engineering. The verification process involved multiple independent artificial intelligence systems examining the same data. Each neural network had been trained using different datasets and optimization techniques, making it unlikely that they would all exhibit the same systematic errors. When 5 separate machine learning systems reached identical conclusions about the artificial nature of the emissions, confidence in the discovery reached scientific certainty. The implications extend beyond this single detection. If artificial intelligence can recognize technological signatures in astronomical data, it opens new avenues for searching for evidence of advanced civilizations throughout the galaxy. Machine learning systems could scan archived observations from decades of astronomical surveys, searching for similar patterns that human researchers might have overlooked. The same algorithms that identified the artificial lights in 3I/A TLAS could discover technological signatures in thousands of other astronomical objects. This discovery also represents a profound moment in human development. The first time our artificial intelligence systems have recognized intelligence originating beyond Earth. The neural networks aboard the Webb telescope achieved a form of first contact, identifying technological patterns created by minds that evolved under distant stars. While we created these artificial intelligence systems, they served as intermediaries in recognizing intelligence that we did not create. The emotional impact of this recognition resonates through the scientific community. For generations, researchers have wondered whether intelligence represents a common feature of cosmic evolution or a rare accident unique to Earth. The detection of artificial patterns in the light from 3I/A TLAS provides compelling evidence that technological development occurs throughout the universe. We are not alone in creating artificial intelligence, engineering sophisticated technologies, or organizing matter according to deliberate designs. As we continue exploring the implications of this discovery, we carry with us the wonder of that initial moment of recognition. Somewhere in the darkness between stars, intelligence has created patterns of light bright enough to cross interstellar distances and complex enough to trigger recognition protocols in our most advanced artificial systems. The universe has revealed itself to be far more interesting and far less lonely than we ever dared imagine. The patterns in the darkness have spoken, and our artificial minds have learned to listen. What messages might they contain? What technologies could create such organized illumination across the vast emptiness of space? These questions guide us deeper into understanding what it means to discover that intelligence transcends the boundaries of worlds, species, and the long night between the stars. Along the quantum pathways that connect distant worlds, information travels not as sound or electricity, but as carefully orchestrated patterns of photons carrying meaning across the cosmic void. The emissions detected by the Webb telescope within 3I/A TLAS speak in frequencies and rhythms that suggest a sophistication far beyond accidental illumination. These signals represent something profound, the first confirmed example of interstellar communication, using light itself as both medium and message. Light serves as the universe's most reliable messenger. Unlike radio waves that can be absorbed by interstellar gas or particle beams that disperse over astronomical distances, photons maintain their integrity across millions of years of travel. The artificial emissions from 3I/A TLAS exploit this fundamental property, encoding information within wavelengths that can traverse the galaxy without degradation. Each photon carries data preserved in its frequency, polarization, and timing, creating a communication system that functions regardless of the medium through which it travels. The spectral analysis reveals a communication protocol of remarkable elegance. Rather than broadcasting across all frequencies simultaneously, the emissions concentrate energy within narrow wavelength bands that correspond to windows of minimal interference. These chosen frequencies avoid absorption by hydrogen, the most abundant element in interstellar space, and circumvent the noise generated by cosmic background radiation. The selection demonstrates deep understanding of galactic physics and suggests long experience with interstellar communication. Decoding the patterns requires understanding how information can be embedded within light waves. The simplest method involves amplitude modulation, varying the brightness of emissions to encode binary data. More sophisticated approaches utilize frequency modulation, phase shifting, and polarization states to increase data density. The signals from 3I/ATLAS employ all these techniques simultaneously, creating a multi-layered communication system that maximizes information transfer while maintaining signal clarity across interstellar distances. The temporal structure of the emissions provides additional insights into their communicative purpose. Natural light sources emit photons randomly, creating statistical fluctuations but no organized patterns. The artificial signals display perfect timing synchronization across multiple frequency bands, indicating centralized control and intentional coordination. Rapid pulse trains alternate with longer interval patterns, suggesting hierarchical data structures similar to packet-based communication protocols used in human-computer networks. Mathematical analysis of the pulse sequences reveals nested periodicities that point toward deliberate encoding schemes. Prime number sequences appear within the timing patterns, a universal mathematical concept that would be recognized by any technological civilization. These mathematical markers serve as synchronization signals, allowing receivers to identify the beginning and end of data packets within the continuous stream of emissions. The sophisticated timing structure suggests not just communication, but communication designed to be decoded by intelligence that might not share the sender's cultural or technological background. The choice of infrared wavelengths for these communications reflects practical considerations for interstellar messaging. Visible light becomes scattered and absorbed by cosmic dust, limiting its range to nearby star systems. Infrared radiation penetrates these obstacles more effectively, maintaining signal strength across thousands of light years. The emissions from 3I/ATLAS concentrate primarily in the near-infrared spectrum, representing an optimal compromise between penetration capability and detection sensitivity. Polarization patterns within the signals add another layer of information encoding. Light waves oscillate in specific orientations, and technological sources can control these polarization states with precision. The artificial emissions display complex polarization sequences that change in coordination with the frequency and amplitude modulations. This three-dimensional encoding dramatically increases data transmission rates, while providing redundancy that ensures message integrity despite interference from magnetic fields and charged particles in interstellar space. The intensity patterns suggest adaptive communication protocols that respond to propagation conditions. During periods when cosmic background radiation increases, the emissions become brighter and more focused. When interstellar conditions favor signal transmission, the intensity decreases while the data rate increases. This adaptive behavior indicates real-time monitoring of signal quality and automatic adjustment of transmission parameters. Sophisticated communication engineering that rivals our most advanced terrestrial systems. Frequency hopping patterns within the signals provide security against interference and demonstrate awareness of potential signal disruption. The emissions regularly shift between different wavelength bands according to pseudo-random sequences that would be difficult for natural phenomena to replicate. This technique prevents cosmic events like stellar flares or gravitational lensing effects from disrupting communication for extended periods. The frequency hopping patterns also suggest multiple simultaneous conversations, with different message streams occupying separate wavelength channels. The coherence properties of the emissions reveal their artificial origins with mathematical certainty. Natural light sources produce incoherent radiation where photon phases remain random relative to each other. The signals from 3I/ATAs demonstrate optical coherence across wavelength ranges, spanning several nanometers, a property that requires sophisticated laser technology or equivalent photonic engineering. This coherence enables complex modulation schemes that would be impossible with incoherent natural light sources. Bandwidth analysis indicates information transmission rates comparable to high-speed terrestrial communication systems. The available frequency spectrum supports data rates measured in gigabits per second, sufficient for transmitting detailed technical information, cultural archives, or real-time sensor data across interstellar distances. The high bandwidth utilization suggests active, ongoing communication rather than simple beacon signals designed merely to announce presence. The discovery of these communication patterns fundamentally changes our understanding of information transfer in the universe. Intelligence need not remain isolated on individual worlds, communicating only within the confines of planetary atmospheres. Advanced civilizations can establish communication networks that span multiple star systems, sharing knowledge and coordinating activities across galactic distances. The signals from 3I/ATAS provide evidence that such networks already exist and that intelligence has learned to speak in the universal language of light. Error correction patterns embedded within the signal structure demonstrate remarkable foresight in communication design. Redundant data packets, cyclic redundancy checks, and forward error correction algorithms ensure message integrity, despite the corruption that inevitably occurs during interstellar transmission. These sophisticated protocols indicate not just technological capability, but experience gained through generations of interstellar communication. The systems have been refined through actual use rather than theoretical development. The implications extend beyond simple message transmission. The complexity and sophistication of these light-based communications suggest coordinated activities requiring real-time information exchange across interstellar distances. Whether organizing exploration missions, sharing scientific discoveries, or coordinating defensive measures, the communication capabilities demonstrated by 3I/ATAs indicate civilization-scale activities that transcend individual worlds. As we contemplate these photonic messages, crossing the darkness between stars, we recognize that light itself has become a bridge between minds separated by impossible distances. The carefully orchestrated emissions from 3I/ATAS speak not just of technological achievement, but of the fundamental drive to communicate that appears to characterize intelligence wherever it emerges. In learning to decode these signals, we take our first steps toward joining a conversation that may have been continuing for millions of years across the galaxy. The language of light offers universal vocabulary for intelligence seeking to communicate across the cosmos. In the patterns detected within 3I/ATAS, we glimpse the syntax and grammar of interstellar discourse, waiting for us to develop fluency in frequencies that speak of wonders beyond our current imagination. Consider the vast electromagnetic spectrum as a cosmic symphony, where each wavelength carries its own voice across the darkness between worlds. While human eyes perceive only the narrow band we call visible light, the universe speaks most eloquently in longer wavelengths that remain hidden from our direct perception. Infrared radiation forms the primary communication channel for advanced civilizations, and the James Webb Space Telescope's unprecedented sensitivity in these invisible frequencies has revealed the first confirmed artificial symphony composed in heat and shadow. Infrared wavelengths offer unique advantages for interstellar communication that become obvious once we understand the physics of galactic space. The interstellar medium contains vast clouds of dust particles that scatter and absorb shorter wavelengths, while allowing infrared radiation to pass through relatively unimpeded. What appears as impenetrable darkness to optical telescopes becomes transparent when observed in infrared, revealing structures and activities that remain hidden from conventional observation. The artificial emissions from 3I/ATAS concentrate primarily in the thermal infrared spectrum, wavelengths between 8 and 12 micrometers that correspond to the radiation emitted by objects at comfortable room temperature. This choice reflects sophisticated understanding of both physics and practicality. These wavelengths penetrate interstellar dust clouds without significant attenuation, maintain signal strength across thousands of light years, and can be generated efficiently using technologies that operate at moderate temperatures. Webb's infrared instruments detected multiple emission bands within the artificial signals, each carrying distinct information streams like instruments in an orchestra. The primary communication channel operates at 10 micrometers, providing high data rates for routine information exchange. Secondary channels at shorter and longer wavelengths carry specialized content, perhaps technical specifications, cultural archives, or emergency communications that require different transmission characteristics. The spectral distribution reveals sophisticated thermal management systems operating within the artificial structures. Natural objects emit infrared radiation in broad, smooth curves determined by their temperature. The artificial sources produce sharp emission peaks at specific wavelengths, indicating technology that concentrates thermal energy into narrow frequency bands. This spectral concentration dramatically increases communication range while minimizing total energy expenditure, an elegant solution to the challenge of interstellar power management. Temperature regulation becomes crucial for maintaining signal quality across interstellar distances. The artificial emissions maintain remarkably stable output levels despite the extreme cold of interstellar space, suggesting advanced thermal control systems that can regulate temperatures within fractions of a degree. Such precision requires sophisticated heat pumps, thermal reservoirs, or possibly superconducting systems that can manipulate heat flow with minimal energy loss. The infrared signatures also reveal information about the materials and construction techniques used in creating these artificial sources. Different materials emit infrared radiation with characteristic spectral signatures that act like fingerprints identifying their composition. The emissions from 3I/ATAs contain features suggesting ceramic composites, metallic alloys, and possibly exotic materials with thermal properties not found in nature. These material signatures provide insights into manufacturing capabilities that far exceed current human technology. Atmospheric considerations play important roles in infrared communication system design. Planetary atmospheres absorb infrared radiation at specific wavelengths, creating windows of transparency interspersed with regions of opacity. The artificial signals from 3I/ATA utilize wavelengths that would penetrate most atmospheric types, suggesting communication systems designed to reach recipients living under various atmospheric conditions. This adaptability indicates experience communicating with civilizations inhabiting different planetary environments. The temporal characteristics of the infrared emissions demonstrate sophisticated modulation techniques adapted to the unique properties of thermal radiation. Unlike radio waves that can be switched on and off instantaneously, thermal sources require time to heat up and cool down. The artificial systems overcome these limitations through rapid thermal switching, using techniques that can modulate infrared output at frequencies measured in kilohertz. Such rapid thermal control requires advanced materials and precision engineering operating at the molecular level. Polarization states within the infrared emissions add additional communication channels that maximize information density. Thermal infrared radiation typically shows minimal polarization, but the artificial signals display complex polarization patterns that change in coordination with intensity and frequency modulations. Creating controlled polarization in thermal radiation requires sophisticated optical elements polarizers, wave plates and beam splitters fabricated to operate efficiently at infrared wavelengths. The power requirements for generating detectable infrared signals across interstellar distances reveal the enormous scale of the technology involved. Thermal radiation follows the inverse square law, becoming exponentially weaker with increasing distance. To maintain signal strength across thousands of light years requires thermal sources operating at power levels measured in terawatts energy outputs, comparable to small nuclear power plants, concentrated into communication systems. Beam collimation techniques allow infrared signals to maintain focus over interstellar distances rather than spreading out in all directions. The artificial emissions from 3I/ATA's display characteristics, suggesting parabolic reflectors or equivalent focusing systems with diameters measured in kilometers. Such massive infrared telescopes would require construction techniques involving materials that maintain precise optical shapes, despite thermal cycling and mechanical stresses in the space environment. The discovery of organized infrared emissions opens new possibilities for detecting artificial activities throughout the galaxy. Natural infrared sources, stars, planets, and interstellar dust emit thermal radiation in predictable patterns determined by their physical properties. Artificial sources create infrared signatures that violate these natural patterns, displaying the same organized characteristics that machine learning systems identified in 3I/ATLS. Future surveys could search archived infrared data for similar signatures, potentially discovering evidence of technological civilizations in thousands of previously examined astronomical objects. Webb's infrared capabilities represent humanity's first opportunity to observe this invisible communication network that may span the galaxy. Our previous astronomical observations, limited to visible light and radio wavelengths, remained blind to the primary communication channels used by advanced civilizations. The infrared emissions from 3I/Atlas may represent routine traffic in a galactic communication network that has operated for millions of years beyond our awareness. The sophisticated thermal engineering demonstrated by these infrared systems suggests civilizations with complete mastery over heat flow and energy management. They can generate, focus, modulate, and control infrared radiation with precision that transforms thermal emission from passive byproduct into active communication tool. Such capabilities indicate technological development that has progressed far beyond our current understanding of thermodynamics and materials science. As we continue developing our own infrared communication technologies, the artificial emissions from 3I/Atlas provide a roadmap for future development. They demonstrate that infrared wavelengths offer practical solutions to the challenges of interstellar communication, providing reliable channels that can operate across galactic distances, despite the obstacles presented by interstellar dust, magnetic fields, and cosmic radiation. The infrared orchestra plays its hidden symphony across the galaxy, with melodies composed in wavelengths of warmth and shadow. In learning to hear these thermal harmonies, we discover that the universe resonates with intelligence that has learned to speak in the invisible frequencies that pervade the cosmos. The artificial emissions from 3I/Atlas invite us to join this cosmic conversation, conducted in the language of heat that bridges the cold darkness between the stars. At precisely 14 hours and 37 minutes Greenwich Mean Time, on a September evening, astronomers working with Webb telescope data encountered something that challenged every assumption about how intelligence organizes itself across vast distances. The artificial lights embedded within 3I/Atlas were not randomly scattered across its surface, nor did they follow the chaotic patterns typical of natural phenomena. Instead, they formed geometric networks with organizational principles that mirror the urban planning and infrastructure design found in advanced technological civilizations. The initial pattern recognition algorithms flagged the geometric arrangements within minutes of processing the spectral data. Grid structures emerged from the seemingly random distribution of emission sources, revealing regular spacing between illumination nodes and systematic connectivity between different regions. These networks displayed characteristics familiar to urban planners and network engineers: a hierarchical organization, redundant pathways, and optimized distribution patterns that maximize coverage while minimizing resource expenditure. The primary network structure consists of major emission nodes connected by chains of smaller light sources, creating a backbone infrastructure that spans the entire observable surface of 3I/Atlas. Secondary networks branch off from this primary system, reaching into regions that would otherwise remain isolated from the main communication grid. The hierarchical organization resembles internet topology, where major routing centers connect to regional hubs that serve local distribution networks. Mathematical analysis reveals optimization principles governing the network layout that match solutions to classical problems in graph theory and operations research. The spacing between nodes follows patterns that minimize total connection length while ensuring redundant pathways between any 2 points in the network. Such optimization requires sophisticated algorithms and careful planning minus characteristics of designed systems rather than evolved structures. The network density varies across different regions of 3I/Atlas in ways that suggest functional specialization. Some areas display closely spaced nodes with high interconnectivity, resembling urban centers with intensive information exchange. Other regions show sparse networks with longer connections, similar to rural infrastructure designed to serve widely distributed populations. These variations indicate purposeful design adapted to different operational requirements across the object's surface. Load balancing mechanisms become apparent when examining the temporal patterns of network activity. During periods of high communication traffic, signals redistribute across multiple pathways to prevent congestion at individual nodes. When network segments experience failures or interruptions, traffic automatically reroutes through alternative connections. Such dynamic load management requires real-time network monitoring and adaptive routing protocols comparable to those used in modern computer networks. The geometric patterns extend beyond two-dimensional surface networks to reveal three-dimensional structures that penetrate deep into 3I/ATLS. Vertical connections link surface nodes to subsurface facilities, creating layered network architectures that maximize utilization of available space. The three-dimensional organization suggests underground cities or industrial complexes connected to surface communication arrays through sophisticated infrastructure networks. Network redundancy levels exceed anything found in human-designed systems, with multiple independent pathways connecting every region to the main communication backbone. The redundancy patterns indicate design criteria that prioritize reliability over efficiency, suggesting systems intended to operate continuously across timescales measured in centuries or millennia. Such robust network architecture requires advanced materials and maintenance systems capable of withstanding the harsh environment of interstellar space. Protocol analysis of the network traffic reveals sophisticated data management systems that coordinate information flow across the entire infrastructure. Different types of data travel along specialized network pathways. High-priority communications use dedicated high-bandwidth connections, while routine information sharing utilizes shared channels with statistical multiplexing. The protocol complexity rivals that of modern internet systems, but operates at speeds and scales that far exceed terrestrial capabilities. The network topology adapts dynamically to changing conditions and requirements, displaying characteristics of self-organizing systems that can reconfigure themselves in response to failures, traffic patterns, or new operational demands. Nodes can join or leave the network without disrupting overall connectivity, and routing paths adjust automatically to maintain optimal performance. Such adaptive capability suggests artificial intelligence systems managing network operations at levels of sophistication beyond current human technology. Quality of service mechanisms ensure that critical communications receive priority treatment regardless of network loading conditions. Emergency signals can commandeer network resources when necessary, while routine traffic yields bandwidth to higher priority data streams. The service differentiation indicates multiple user classes or application types sharing the same network infrastructure, as evidence of complex organizational structures utilizing the communication systems. Security features embedded within the network architecture protect against both accidental interference and intentional intrusion attempts. Encrypted communication channels prevent unauthorized access to sensitive information, while authentication protocols ensure that only authorized users can inject traffic into the network. The security sophistication suggests awareness of potential threats and long experience with network protection in contested environments. The power distribution system that energizes the network displays engineering principles that optimize energy delivery across vast distances while minimizing transmission losses. High-capacity power trunks feed regional distribution centers that serve local network clusters, creating hierarchical power architectures that mirror the communication network topology. The power management sophistication indicates complete integration between communication and energy systems. Network synchronization mechanisms maintain precise timing coordination across all nodes, despite the light speed delays inherent in spanning distances of hundreds of kilometers. Distributed timing protocols ensure that network operations remain synchronized even when communication delays prevent centralized control. The timing precision achieved across such distances requires advanced clock synchronization techniques operating at levels of accuracy measured in nanoseconds. The discovery of these organized networks fundamentally changes our understanding of how intelligence can scale across cosmic distances. Rather than remaining confined to planetary surfaces, advanced civilizations can create distributed infrastructures that transform entire space objects into coordinated technological systems. The networks within 3I/ATLAS demonstrate that intelligence can organize itself at scales previously thought impossible. Fault tolerance mechanisms built into the network architecture ensure continued operation despite the inevitable failures that occur in systems operating across cosmic timescales. Automated repair systems can isolate failed components and reconfigure network pathways to maintain connectivity. The fault tolerance levels suggest systems designed to operate independently for extended periods without external maintenance or intervention. The organizational principles revealed by these networks provide insights into the social and technological structures of the civilization that created them. The careful resource allocation, sophisticated coordination mechanisms, and robust reliability features suggest highly organized societies with long-term planning capabilities and advanced cooperative behaviors. Such networks require sustained effort across many generations to design, construct, and maintain. As we study these cosmic infrastructures, we gain new perspectives on the potential for intelligence to reshape its environment on truly astronomical scales. The networks within 3I/Atlas represent urban planning extended to space objects, transforming raw celestial bodies into organized technological ecosystems. They demonstrate that intelligence can impose order on chaos, creating structured environments that support complex activities across interstellar distances. The void between stars need not remain empty and unorganized. Intelligence can fill it with networks that connect minds, coordinate activities, and enable cooperation across distances that separate entire star systems. In the geometric patterns detected within 3I/Atlas, we glimpse the infrastructure of galactic civilization networks in the void that transform empty space into organized technological environments, supporting intelligence on truly cosmic scales. Every photon detected by the Webb telescope from 3I/Atlas began its journey as energy concentrated, shaped, and directed across interstellar distances with precision that defies conventional understanding of power generation and transmission. The artificial illumination patterns require energy outputs measured not in kilowatts or megawatts, but in terawatts sustained continuously across cosmic timescales. This presents us with a profound paradox. How does any civilization generate and manage power at levels that rival the energy output of entire stars? The fundamental physics of electromagnetic radiation across interstellar distances imposes harsh requirements on any artificial light source. The inverse square law ensures that signal strength decreases dramatically with distance, requiring exponentially higher power outputs to maintain detectable signals across thousands of light years. Simple calculations reveal that creating the illumination patterns detected in 3I/Atlas requires power generation capabilities that exceed the total energy production of human civilization by factors of millions. The energy density requirements become even more staggering when we consider the concentrated nature of the artificial emissions. Rather than spreading power across broad wavelength ranges like natural thermal sources, the artificial systems concentrate energy into narrow frequency bands and specific beam directions. This concentration amplifies the effective signal strength, but requires power management technologies that can handle energy densities approaching those found in stellar cores. Examining the temporal stability of the emissions provides additional insights into the energy generation systems. The artificial lights maintain constant output levels across observation periods spanning weeks, with variations of less than 1% in overall brightness. Such stability indicates power sources with enormous energy reserves or extremely efficient energy storage and regulation systems. Natural energy sources, including nuclear fusion reactions, display inherent variability that would create detectable fluctuations in the output signals. The geographical distribution of power consumption across 3I/Atlas reveals sophisticated energy management infrastructures. High power emission nodes cluster in specific regions, while being connected through lower power distribution networks to peripheral areas. The power distribution pattern suggests centralized generation facilities feeding hierarchical distribution systems that deliver energy where needed while minimizing transmission losses. Such organization requires advanced power grid technologies operating at scales that dwarf terrestrial electrical systems. Thermal management becomes a critical challenge when handling power at these enormous scales. The laws of thermodynamics dictate that energy conversion processes generate waste heat that must be dissipated to prevent system failures. The artificial structures within 3I/Atlas must possess thermal management capabilities that can handle heat flows measured in terawatts, while maintaining operating temperatures compatible with complex electronics and mechanical systems. The spectral characteristics of the emissions provide clues about the energy conversion mechanisms involved. The narrow wavelength bands and coherent properties suggest systems that can convert raw power into highly organized electromagnetic radiation with minimal waste. Such conversion efficiency requires technologies that approach the theoretical limits imposed by quantum mechanics energy conversion systems with efficiencies exceeding 99% across power levels that challenge our understanding of materials science. Load balancing across the network infrastructure indicates dynamic power management systems that can redistribute energy in response to changing demands and system conditions. When communication traffic increases in specific network regions, power flows automatically increase to support the higher activity levels. When systems fail or require maintenance, power reroutes to alternative pathways without interrupting overall network operations. Such dynamic power management requires real-time monitoring and control systems operating at speeds measured in microseconds. The sustained nature of the power output over cosmic timescales suggests energy sources with longevity that exceeds conventional power generation technologies. Chemical fuels would be exhausted within days at these power levels. Nuclear fission systems might operate for decades before requiring fuel replacement. Even fusion reactions using hydrogen would consume available fuel within centuries. The multi-million-year operational timescales implied by interstellar travel require energy sources with capabilities that transcend conventional nuclear physics. Power transmission across the vast networks within 3I/ATAS presents engineering challenges that push the boundaries of electrical engineering. Superconducting power lines could eliminate resistive losses, but require maintenance of cryogenic temperatures across thousands of kilometers. Microwave power transmission could beam energy through space without physical conductors, but requires enormous transmitting and receiving antennas to maintain efficiency at these scales. Energy storage systems must buffer power generation and consumption across operational cycles that span astronomical timescales. The artificial systems within 3I/ATLAS may operate continuously for millions of years during their journey through interstellar space, requiring energy storage technologies with essentially unlimited operational lifetimes. Such storage systems must maintain their capacity despite cosmic radiation, temperature cycling, and the gradual degradation that affects all physical systems. The power generation technologies implied by these energy requirements suggest civilizations with complete mastery over fundamental physical processes. They may have developed controlled fusion systems that approach the energy densities found in stellar cores, antimatter reactors that convert matter directly into energy with perfect efficiency, or exotic energy extraction methods that tap into quantum vacuum fluctuations or gravitational fields. Waste heat management at these power levels requires innovative approaches to thermal dissipation. Conventional cooling systems become inadequate when handling terawatt power flows. The artificial structures may employ radiative cooling systems with enormous surface areas, phase change cooling using materials with exceptional thermal properties, or possibly exotic cooling techniques that manipulate thermal energy at the molecular level. The integration of power systems with communication and network infrastructures demonstrates sophisticated systems engineering that coordinates energy distribution with information flow. Power allocation automatically adjusts to support communication requirements, ensuring that network performance remains optimal regardless of energy availability. The tight coupling between power and communication systems suggests design approaches that treat energy and information as complementary resources requiring coordinated management. Backup power systems provide redundancy that ensures continued operation despite failures in primary power generation facilities. Multiple independent power sources can substitute for each other, maintaining network operations even if major power plants experience outages. The backup system capacity approaches the levels of primary power generation, indicating civilizations with energy resources so abundant that maintaining multiple redundant power infrastructures represents acceptable overhead costs. The discovery of these energy signatures fundamentally challenges our understanding of what civilizations can achieve through technological development. The power levels demonstrated by 3I/ATLAS approach those of natural cosmic phenomena, stellar output, galactic magnetic fields, and gravitational energy sources. This suggests civilizations that have learned to harness energy sources operating at astronomical scales, transforming from planetary energy consumers into cosmic energy manipulators. As we contemplate the implications of these enormous power requirements, we recognize that advanced civilizations must eventually transcend the energy limitations that constrain planetary societies. The artificial illumination within 3I/ATLAS provides evidence that intelligence can indeed overcome these limitations, developing energy technologies that enable activities and communications across interstellar distances. The energy paradox challenges us to expand our concepts of what becomes possible when civilizations gain complete mastery over the fundamental forces that power the universe. The patterns of light crossing interstellar space carry with them the signatures of energy technologies that transform matter and space into resources for sustaining intelligence across cosmic distances and timescales. In learning to read these energy signatures, we glimpse the technological capabilities that may await any civilization willing to pursue mastery over the forces that govern reality itself. What engineering principles allow civilization to reshape light itself, transforming scattered photons into coherent beams capable of crossing the galaxy with information intact? The artificial illumination detected within 3I/Atlas reveals evidence of optical engineering on scales that dwarf earthly technologies. Mirror systems and light-focusing installations that can collect, concentrate, and redirect electromagnetic radiation with precision measured in wavelengths across distances measured in kilometers. The coherence properties of the artificial emissions provide compelling evidence for massive mirror arrays operating within the structure of 3I/Atlas. Natural light sources emit incoherent radiation where individual photons maintain random phase relationships with each other. The artificial signals display optical coherence across wavelength ranges, spanning several micrometers, micromometers, a property that requires either laser-like emission sources or sophisticated beam combination systems that can merge multiple light sources into coherent output beams. The focusing requirements for interstellar communication demand optical systems with apertures measured in kilometers rather than meters. Simple calculations based on diffraction limits reveal that maintaining narrow beam patterns across interstellar distances requires primary mirrors or equivalent optical elements with diameters exceeding those of the largest terrestrial radio telescopes. Such enormous optical systems must maintain surface accuracy measured in fractions of wavelengths despite thermal cycling, mechanical stresses, and the particle bombardment prevalent in interstellar space. The spectral characteristics of the emissions suggest active optical systems that can dynamically adjust their focusing properties in response to changing communication requirements. Different wavelength bands display different beam patterns and collimation properties, indicating optical elements that can provide wavelength-dependent focusing minus sophisticated diffractive optics or adaptive mirror systems with surface configurations that change according to operational needs. The beam steering capabilities become evident when examining how the artificial signals maintain optimal pointing, despite the complex rotational dynamics of 3I/Atlas during its journey through space. The emissions consistently point toward specific regions of space rather than remaining fixed relative to the object's surface, suggesting gimbaled mirror systems or equivalent beam steering technologies that can track targets with precision measured in microarc seconds across interstellar distances. The thermal management challenges associated with high-power optical systems operating in space require innovative engineering solutions. Mirrors handling terawatt power levels must dissipate enormous thermal loads while maintaining the surface accuracy necessary for coherent beam formation. The artificial systems within 3I/Atlas may employ mirrors fabricated from materials with exceptional thermal conductivity, active cooling systems that regulate surface temperatures, or possibly exotic optical elements that reflect light without absorbing energy. Adaptive optic systems appear necessary to compensate for the optical distortions introduced by interstellar medium interactions and gravitational effects during the long journey through space. The coherent properties of the detected signals suggest real-time correction systems that can adjust mirror surfaces to maintain optimal beam quality despite the constantly changing optical conditions encountered during interstellar travel. Such adaptive systems require wavefront sensors and mirror actuators operating at speeds measured in milliseconds across optical elements spanning kilometers. The polarization control demonstrated within the artificial emissions indicates sophisticated optical systems that can manipulate light polarization states with precision across multiple wavelength bands simultaneously. Creating controlled polarization patterns requires specialized optical elements, waveplates, polarizers, and retarders fabricated to operate efficiently at the wavelengths used for interstellar communication. The polarization complexity suggests optical systems that can simultaneously generate multiple independent communication channels using different polarization states. Multi-layered mirror systems may account for the sophisticated spectral shaping observed in the artificial emissions. Different mirror coatings optimized for specific wavelength ranges could be combined in hierarchical arrangements that provide optimal reflectivity across the broad spectral bands used for communication. Such multi-layer systems require precise manufacturing techniques that can control optical properties at the atomic level across mirror surfaces measured in square kilometers. The power handling capabilities of these optical systems exceed anything found in terrestrial technology by orders of magnitude. Mirrors that can reflect terawatt power levels without damage require materials with exceptional optical and thermal property, possibly exotic materials with superconducting properties, metamaterials with engineered optical responses, or composite structures that combine multiple materials to achieve properties unavailable in naturally occurring substances. Segmented mirror architectures may enable the construction of optical systems at the enormous scales required for interstellar communication. Individual mirror segments fabricated to high precision could be assembled into composite optical systems with effective apertures measured in kilometers. Such segmented systems require precise alignment and phasing control to maintain coherent beam formation across thousands of individual optical elements operating in coordination. The automated manufacturing and maintenance systems necessary to construct and operate these optical installations represent technological capabilities that far exceed current human engineering. Building kilometer-scale mirror systems in space requires robotic fabrication facilities, automated quality control systems, and self-repair capabilities that can maintain optical precision across operational timescales measured in millions of years. Such automated systems must operate independently without external support or intervention. Optical metrology systems provide the precision measurement capabilities necessary to maintain mirror surface accuracy and alignment across these enormous optical installations. Interferometric measurement techniques operating at wavelengths shorter than the communication frequencies can detect surface deviations measured in nanometers across distances spanning kilometers. The metrology sophistication required suggests measurement and control technologies that approach fundamental quantum limits on optical precision. The integration of optical systems with power generation and distribution networks demonstrates sophisticated systems engineering that coordinates energy flow with optical performance requirements. Power allocation automatically adjusts to support optimal optical system operation, providing additional energy during periods requiring maximum beam quality while conserving power when communication demands allow reduced performance. Such integration requires control systems that treat optical and electrical systems as components of unified technological infrastructures. Beam combination techniques allow multiple smaller optical systems to function as single large apertures, providing flexibility and redundancy while maintaining the optical performance of monolithic systems. Coherent beam combination requires precise phase control across multiple optical channels, maintaining wavelength scale accuracy in optical path lengths despite mechanical vibrations and thermal variations. The beam combination sophistication suggests optical control technologies operating at the limits imposed by quantum mechanics. The discovery of these optical engineering capabilities fundamentally expands our understanding of what becomes possible when civilizations develop mastery over electromagnetic radiation. Rather than remaining passive recipients of natural light, advanced civilizations can actively manipulate photons to serve technological purposes that span interstellar distances. The mirror systems within 3I/8 LARS demonstrate that intelligence can indeed engineer light itself. As we contemplate these cosmic optical installations, we recognize that space offers unique advantages for optical engineering that remain unavailable on planetary surfaces. The absence of atmospheric turbulence, gravitational uniformity, and unlimited space for large constructions enable optical systems with capabilities that transcend Earth-bound limitations. Advanced civilizations may routinely construct optical installations in space that dwarf the largest terrestrial telescopes. The mirrors across the cosmos reshape our understanding of how intelligence can extend its reach beyond the limitations of individual worlds. By learning to engineer light with precision and power that rival natural cosmic phenomena, civilizations can create communication networks that span the galaxy, turning space itself into a medium for coordinated activities across interstellar distances. In the coherent beams detected within 3I/A Tellus, we glimpse the optical technologies that may eventually connect all intelligence within our galaxy into unified technological networks operating at truly cosmic scales. These optical installations represent more than mere communication systems. They demonstrate that intelligence can impose technological order on electromagnetic radiation itself, transforming light from natural phenomenon into engineered resource, serving the purposes of minds that have learned to shape reality according to their designs. Beneath the steady glow of artificial illumination within 3I/A TLRs lies a deeper rhythm, precise temporal patterns that pulse with the regularity of cosmic chronometers, yet display variations too organized to result from natural processes. These synchronized emissions beat with rhythms that suggest not mere illumination, but intentional signaling designed to attract attention across the vast darkness that separates intelligent civilizations dwelling among different stars. The temporal analysis of the artificial emissions reveals multiple overlapping periodicities operating simultaneously across different timescales. Rapid pulse trains with frequencies measured in kilohertz provide high-speed data channels for detailed information exchange. Slower rhythmic patterns operating at intervals of minutes or hours may coordinate long-term activities or provide timing references for distributed operations. The hierarchical timing structure resembles the nested clock systems used in complex technological networks, but operates at precision levels that exceed earthly timekeeping capabilities. Mathematical analysis of the pulse sequences reveals patterns that cannot occur naturally. Prime number sequences appear in the timing intervals, providing universal mathematical markers that any technological civilization would recognize as artificial. Fibonacci progressions, geometric series, and other mathematical relationships manifest within the temporal structure, creating patterns that serve as unambiguous signatures of intelligent design, while simultaneously encoding information within their numerical relationships. The synchronization accuracy across different emission sources within 3I/A TLRs approaches the limits imposed by fundamental physics. Despite spanning distances of hundreds of kilometers, individual light sources maintain timing coordination with precision measured in nanoseconds, minus accuracy levels that require atomic clock standards and sophisticated signal distribution networks. Achieving such synchronization across space-based systems requires timing technologies that surpass the capabilities of terrestrial precision timing networks. Phase relationships between different pulse trains provide additional evidence of coordinated signaling systems. Multiple emission sources maintain specific phase offsets that create interference patterns and signal enhancement effects when observed from particular directions in space. The phase coordination suggests beacon systems designed to maximize signal strength towards specific target regions while minimizing energy waste in non-productive directions. Such directional signaling requires precise knowledge of target locations and sophisticated beam-forming technologies. The pulse modulation techniques demonstrate advanced signal processing capabilities that can encode complex information within simple timing patterns. Pulse width modulation varies the duration of individual pulses to carry digital data, while pulse position modulation encodes information within the precise timing of pulse occurrences. Multiple modulation techniques operate simultaneously within the same pulse trains, creating multiplexed communication channels that maximize information density within available bandwidth. Error correction patterns embedded within the pulse sequences ensure signal integrity despite the corruption that inevitably occurs during interstellar transmission. Redundant pulse patterns, checksums, and forward error correction algorithms protect against data loss while providing mechanisms for receivers to identify and correct transmission errors. The sophistication of these error correction systems indicates extensive experience with long-distance communication in environments prone to interference and signal degradation. Adaptive timing protocols adjust pulse patterns in response to changing propagation conditions and communication requirements. During periods when interstellar conditions favor signal transmission, pulse rates increase to maximize data throughput. When cosmic events create interference or signal blockages, the systems automatically reduce data rates while increasing error correction overhead to maintain communication reliability. Such adaptive capabilities require real-time analysis of channel conditions and dynamic adjustment of transmission parameters. The discovery of beacon-like characteristics within the pulse patterns suggests signaling systems designed specifically to attract attention from distant observers. Certain pulse sequences repeat at regular intervals, with timing patterns that would be impossible to generate naturally, creating unmistakable signatures of technological origin. These beacon signals may serve as initial contact protocols, designed to announce the presence of technological civilization to any observers capable of detecting artificial timing patterns. Frequency analysis of the pulse trains reveals sophisticated spread spectrum techniques that distribute signal energy across multiple frequency bands to prevent interference and improve signal reliability. The frequency hopping patterns follow pseudo-random sequences that would be difficult for natural phenomena to replicate, while providing communication channels that remain robust against both accidental interference and intentional jamming attempts. Such techniques indicate awareness of potential signal disruption and experience with communication security in contested environments. The power management systems that drive these pulsing emissions demonstrate remarkable efficiency in energy utilization. Rather than maintaining constant power output, the systems concentrate energy into brief, intense pulses that achieve higher peak signal strength while consuming less total energy than continuous transmission systems. The pulse shaping techniques optimize signal-to-noise ratios while minimizing power consumption, engineering approaches that maximize communication range while conserving energy resources. Network synchronization protocols coordinate timing across the entire communication infrastructure within 3I/RT layers, ensuring that distributed pulse generators operate as components of unified signaling systems. Master timing references distribute synchronization signals throughout the network, while local timing systems maintain accuracy between synchronization updates. The distributed timing architecture provides redundancy and fault tolerance while maintaining system-wide coordination across equipment spanning hundreds of kilometers. The temporal patterns also reveal information about the operational cycles and activity patterns of the systems generating these signals. Certain pulse sequences occur only during specific time periods, suggesting scheduled communications, maintenance cycles, or responses to external events. The activity patterns provide insights into the organizational structures and operational procedures of the civilization that created these communication systems. Signal authentication mechanisms embedded within the pulse patterns prevent unauthorized users from injecting false signals into the communication networks. Cryptographic techniques create unique pulse signatures that can be verified by authorized receivers while remaining undetectable to eavesdroppers. The authentication sophistication suggests security-conscious civilizations with experience in protecting communication systems from intrusion attempts. The multi-layered nature of the pulse patterns enables simultaneous communication across multiple channels operating at different timescales. High-speed pulse trains carry routine data traffic, while longer period patterns may coordinate strategic planning or emergency communications. The temporal multiplexing techniques maximize utilization of available communication resources while providing service differentiation for different types of information. The synchronized nature of these pulses across interstellar distances suggests communication networks that extend far beyond the boundaries of 3I/AT itself. The timing references and coordination protocols may synchronize with similar systems operating within other space objects or installations throughout the galaxy. Such coordination capabilities indicate communication networks operating at scales that encompass multiple star systems. As we observe these cosmic chronometers pulsing with artificial precision across the darkness, we recognize that intelligence has learned to impose temporal order on electromagnetic radiation, transforming random photon emission into organized communication protocols. The synchronized pulses within 3I/AT represent lighthouses in space mice beacons that announce the presence of technological civilization while simultaneously providing communication channels for coordinated activities across interstellar distances. These temporal patterns demonstrate that intelligence need not remain isolated within individual star systems, communicating only with local neighbors. The synchronized pulse networks detected within 3I/AT suggest galactic communication systems that coordinate activities across distances and timescales that encompass entire regions of the galaxy, turning space itself into a vast timing network that enables cooperation between civilizations separated by hundreds of light years. Within the depths of space surrounding 3I/Etelas, reality itself may not be what it appears to be. The artificial illumination detected by Webb's sensitive instruments might not originate from physical structures at all, but rather from three-dimensional light fields projected into empty space through technologies that transform electromagnetic radiation into apparent matter. These holographic possibilities suggest civilizations that have learned to manipulate the fundamental relationship between energy and information, creating detectable phenomena without requiring traditional physical substrates. The optical characteristics of the artificial emissions contain subtle signatures that distinguish projected light from light emitted by physical sources. Real objects illuminated by external light sources create predictable shadow patterns and reflection characteristics determined by their material properties and surface geometries. The artificial illumination within 3I/Etelas displays optical properties that suggest self-illuminating phenomena rather than reflected or transmitted light from conventional physical structures. Holographic projection technologies can create three-dimensional light distributions that appear solid and substantial to distant observers while containing no actual matter. The projected light fields interact with electromagnetic radiation in ways that mimic physical objects, creating spectral signatures and polarization patterns that suggest material structures. Advanced holographic systems could project apparent buildings, machinery, or entire technological installations across space without requiring the enormous masses and construction efforts needed for physical infrastructure. The energy requirements for large-scale holographic projections across the distances involved within 3I/Etelas represent significant technological challenges, but ones that may prove more manageable than constructing equivalent physical structures. Holographic systems require power to generate and maintain the projected light fields, but avoid the material costs and structural engineering challenges associated with building actual physical installations spanning hundreds of kilometers in space. Plasma manipulation technologies may provide the physical basis for creating holographic projections that can persist in the space environment. Controlled plasma formations can emit coherent electromagnetic radiation while maintaining organized structures across extended time periods. Advanced civilizations might have developed plasma control techniques that can shape ionized gases into complex three-dimensional patterns that serve as sources for projected light displays. The temporal stability of the artificial emissions suggests holographic systems with remarkable persistence and coherence across time periods, spanning weeks or months. Maintaining complex three-dimensional light field distributions requires precise control over amplitude, phase, and polarization characteristics of numerous projected beams operating simultaneously. Such stability indicates holographic technologies with capabilities that far exceed current terrestrial systems used for entertainment and display applications. The spectral complexity of the emissions indicates holographic projection systems that can simultaneously generate multiple wavelength distributions within the same spatial regions. Different spectral components may carry independent information streams or serve specialized functions within the overall projected display. Multi-wavelength holographic projection requires sophisticated optical systems that can generate and control coherent light across broad spectral ranges while maintaining precise spatial registration between different wavelength components. Interference patterns within the artificial illumination provide evidence for holographic beam combination techniques that merge multiple coherent light sources into unified projected displays. The constructive and destructive interference effects create spatial intensity distributions that suggest multiple projection sources operating in coordination to generate complex three-dimensional light field patterns. Such beam combination techniques require precision phase control and spatial alignment that challenge the limits of optical engineering. The adaptive characteristics of the emissions suggest holographic systems that can modify their projected displays in response to changing conditions or communication requirements. Real-time holographic projection requires computational capabilities that can calculate and update three-dimensional light field distributions at rates measured in milliseconds while maintaining spatial and temporal coherence across enormous projected volumes. Quantum holographic techniques may enable projection systems that operate according to principles beyond classical electromagnetic theory. Quantum entanglement between projected photons could create correlated light fields that maintain coherence across distances that exceed classical limitations. Quantum holographic systems might achieve projection capabilities that transcend the constraints imposed by classical physics on light field generation and control. The power distribution patterns within the projected displays suggest holographic systems with sophisticated beam-forming capabilities that can concentrate projection energy into specific spatial regions while minimizing energy waste in unproductive areas. Adaptive beam forming adjusts projection intensity and focus in real time to optimize display quality while conserving energy resources. Such optimization requires feedback control systems that can monitor display characteristics and adjust projection parameters accordingly. Virtual matter techniques may allow holographic projections to exhibit apparent physical properties that mimic real material structures. Projected light fields that interact with electromagnetic radiation in ways that simulate material properties could create apparent objects that display temperature signatures, polarization effects, and spectral characteristics indistinguishable from physical structures to distant observers using electromagnetic sensors. The maintenance requirements for large-scale holographic projection systems operating in space present unique engineering challenges. Unlike physical structures that can be repaired using conventional construction techniques, holographic systems require continuous power and precise optical control to maintain their projected displays. The long-term stability of the emissions from 3I/ATLS suggests maintenance capabilities that can sustain complex projection systems across operational timescales measured in years or decades. The information processing requirements for generating complex three-dimensional holographic displays exceed the computational capabilities of conventional systems by enormous factors. Creating realistic projected environments requires real-time calculation of light field distributions across millions of spatial coordinates while maintaining temporal coherence across time periods spanning hours or days. Such computational demands suggest information processing technologies with capabilities that approach fundamental physical limits on computation density and speed. The discovery of possible holographic technologies within 3I/ATLA fundamentally challenges our understanding of how intelligence can create detectable phenomena across interstellar distances. Rather than requiring enormous physical constructions, advanced civilizations may achieve their technological objectives through projected displays that can be modified, relocated, or reconfigured according to changing requirements without the limitations imposed by physical matter. Stealth capabilities inherent in holographic projection systems provide strategic advantages for civilizations operating in environments where concealment may be desirable. Holographic displays can be activated or deactivated instantly, relocated without physical movement, or modified to present different apparent characteristics to different observers. Such capabilities offer flexibility and security advantages that surpass those available through conventional physical technologies. The implications of holographic projection technologies extend beyond simple communication or display applications. Entire technological infrastructures might exist as projected phenomena rather than physical constructions, enabling civilizations to create apparent industrial complexes, transportation systems, or research facilities without the material costs and construction challenges associated with physical development. Such capabilities would fundamentally transform how advanced civilizations approach engineering and infrastructure development. As we contemplate these possibilities of projected reality within 3I/ATLS, we recognize that the boundary between energy and matter may prove more flexible than previously imagined. Holographic projection technologies suggest that intelligence can create apparently physical phenomena through sophisticated manipulation of electromagnetic fields, transforming space itself into a canvas for technological creativity that transcends the limitations imposed by conventional matter and energy relationships. The holographic projections crossing interstellar space challenge us to expand our concepts of what constitutes reality in environments where advanced technologies can reshape the fundamental relationship between information, energy, and apparent physical existence. In the projected light fields detected within 3I/ATLS, we glimpse technologies that may eventually allow any civilization to create reality according to its designs rather than being constrained by the limitations of naturally occurring matter. Every technological process generates waste heat as an inevitable consequence of the laws of thermodynamics. Yet the thermal signatures emanating from the artificial structures within 3I/ATLS violate every prediction about how advanced machinery should manage energy conversion and heat dissipation. The infrared emissions display temperature patterns that suggest thermal management systems operating according to principles that transcend conventional engineering approaches, revealing technologies that can manipulate heat flow with precision that approaches theoretical perfection. The fundamental challenge of thermal management at the power levels required for interstellar communication becomes apparent when we consider the enormous energy flows involved. Systems generating terawatt power outputs must dissipate equivalent amounts of waste heat to prevent catastrophic overheating. Natural thermal radiation follows the Stefan-Boltzmann law, requiring enormous surface areas to radiate away such prodigious heat loads. Yet the thermal signatures from 3I/ATAA suggest compact systems that violate conventional heat dissipation relationships. The spectral characteristics of the thermal emissions reveal temperature distributions that defy explanation through conventional heat transfer mechanisms. Rather than displaying the smooth thermal curves expected from objects in thermal equilibrium, the signatures show sharp temperature gradients and localized hotspots that suggest active thermal control systems. These patterns indicate technologies that can direct heat flow with precision, concentrating thermal energy into specific regions while maintaining other areas at substantially different temperatures. Advanced superconducting systems may provide one explanation for the anomalous thermal behavior observed within 3I/ATLAS. Superconducting materials can carry enormous electrical currents without generating resistive heating, potentially enabling power transmission and processing at levels that would destroy conventional conductors. However, maintaining superconducting conditions requires cryogenic temperatures that create additional thermal management challenges when operating in space environments exposed to solar radiation and other heat sources. Quantum thermal engineering techniques may enable heat management capabilities that transcend classical thermodynamics limitations. Quantum heat engines can achieve efficiency levels that approach the theoretical Carnot limit, while quantum refrigeration systems might provide cooling capabilities that exceed conventional heat pumps. Such quantum thermal technologies could explain the remarkable thermal control evidenced by the heat signatures from 3I/ATLAS. The spatial distribution of thermal emissions suggests hierarchical cooling systems that can manage heat flow across multiple scales simultaneously. Large-scale thermal management systems handle overall heat balance and dissipation, while local thermal control systems regulate temperatures within specific equipment or operational areas. The hierarchical approach provides thermal regulation precision that enables optimal performance across diverse operational requirements within the same technological infrastructure. Thermal metamaterials with engineered heat transfer properties may enable thermal management capabilities unavailable through conventional materials. Metamaterials can be designed to exhibit thermal conductivities that vary with direction, temperature, or frequency, enabling sophisticated thermal control systems that can direct heat flow along predetermined pathways while providing thermal isolation between different system components. Such materials could explain the complex thermal patterns observed within 3I/ATLAS. Phase change cooling systems utilizing materials with exceptional thermal properties may provide thermal management capabilities that exceed conventional cooling technologies. Materials that undergo phase transitions absorb or release enormous amounts of thermal energy while maintaining constant temperatures, providing thermal buffering that can smooth out temporal variations in heat generation. Advanced phase change materials with engineered properties could provide thermal management capabilities that enable sustained high-power operations. The temporal characteristics of the thermal emissions reveal thermal management systems with remarkable response speeds and precision. Temperature variations occur within timeframes measured in seconds, suggesting thermal control systems that can rapidly adjust heat flow in response to changing operational requirements. Such rapid thermal response requires materials with exceptional thermal conductivity and control systems with response speeds that approach fundamental limits imposed by heat transfer physics. Thermoelectric energy conversion systems may provide both cooling and power generation capabilities that contribute to the overall energy efficiency of the artificial systems within 3I/ATLAS. Thermoelectric materials can convert waste heat directly into electrical power, while simultaneously providing cooling effects, creating integrated thermal management systems that recover energy from waste heat rather than simply dissipating it. Advanced thermoelectric materials with high efficiency could significantly improve overall system energy balance. Radiative cooling systems with sophisticated surface treatments may enable enhanced heat dissipation capabilities that exceed conventional thermal radiation limits. Engineered surface structures can modify emissivity and thermal radiation patterns, enabling more efficient heat rejection while maintaining optimal operating temperatures. Advanced radiative cooling systems might utilize nanostructured surfaces or active thermal control elements that can adjust radiation characteristics according to cooling requirements. The integration of thermal management systems with power generation and distribution networks demonstrates sophisticated systems engineering that coordinates thermal and electrical systems as unified technological infrastructures. Waste heat from power generation systems provides thermal energy for heating applications, while cooling systems utilize electrical power to maintain optimal operating temperatures. The thermal-electrical integration achieves overall system efficiencies that exceed those possible through independent thermal and electrical systems. Thermal energy storage systems may provide thermal buffering capabilities that enable sustained high-power operations despite variations in power generation or cooling capacity. Advanced thermal storage materials can absorb excess thermal energy during periods of high heat generation and release stored thermal energy when additional heating is required. Such thermal energy storage provides operational flexibility while maintaining thermal stability across varying operational demands. The waste heat recovery systems suggested by the thermal signatures may achieve energy recycling efficiencies that approach theoretical limits. Rather than treating waste heat as an unavoidable loss, advanced thermal management systems can recover and reuse thermal energy for productive purposes, creating closed-loop thermal cycles that maximize energy utilization efficiency. Such heat recovery capabilities could significantly reduce overall energy requirements while improving system reliability. Thermal signature masking technologies may enable thermal management systems that can control their infrared emissions to prevent detection or provide misleading thermal information to external observers. Variable emissivity surfaces, thermal cloaking systems, or controlled thermal emission patterns could provide stealth capabilities or deception techniques that offer strategic advantages in environments where thermal detection poses security concerns. The discovery of these advanced thermal management capabilities fundamentally changes our understanding of what becomes possible when civilizations achieve mastery over heat transfer and thermal control. Rather than being constrained by conventional thermal limitations, advanced civilizations can engineer thermal systems that approach theoretical limits on thermal management efficiency, enabling technological capabilities that transcend earthbound thermal engineering limitations. As we study these mysterious thermal signatures, we recognize that thermal management represents a fundamental enabling technology that determines the ultimate capabilities of any advanced technological civilization. The thermal control systems evidenced within 3I/8 demonstrate that intelligence can indeed overcome the thermal limitations that constrain conventional technologies, developing thermal management capabilities that enable sustained high-power operations across interstellar timescales. The heat signatures crossing space reveal more than mere thermal management. They demonstrate that advanced civilizations have learned to manipulate thermal energy as precisely as they control electrical power or electromagnetic radiation. In mastering heat flow, intelligence gains access to energy utilization efficiencies that may be essential for sustaining technological activities across the enormous scales of space and time that characterize interstellar operations. These thermal technologies suggest that the boundaries between waste heat and useful energy become flexible when civilizations develop complete mastery over thermal physics, transforming thermal management from engineering constraint into enabling technology that supports capabilities limited only by fundamental physical laws rather than practical engineering limitations. The confirmation that artificial lights pulse within 3I/8 as it journeys through our solar system represents far more than a single astronomical discovery. It constitutes the first unambiguous evidence that intelligence has transcended planetary boundaries to create technological infrastructures spanning interstellar distances. This revelation fundamentally transforms our understanding of what intelligence can achieve when it commits to engineering projects across cosmic scales, and what this means for humanity's future among the stars. The detection of these artificial signatures provides definitive answers to questions that have shaped human philosophy for millennia. We are not alone in developing technology sophisticated enough to modify our environment according to deliberate designs. Intelligence appears to be a recurring feature of cosmic evolution, arising independently in multiple star systems and developing technological capabilities that enable communication and coordination across galactic distances. The universe reveals itself to contain minds that have learned to reshape matter and energy at scales that encompass entire space objects. The implications for astrobiology extend far beyond simple confirmation of extraterrestrial intelligence. The artificial structures within 3I/ATLAS demonstrate that advanced civilizations can create self-sustaining technological ecosystems that operate independently across the millions of years required for interstellar travel. This suggests that intelligence can indeed escape the limitations of individual planets, creating distributed technological networks that persist across cosmic timescales while maintaining sophisticated operational capabilities. The discovery fundamentally alters the scientific framework for searching for evidence of technological civilizations throughout the galaxy. Rather than focusing exclusively on radio signals or planetary atmospheric signatures, astronomers must now consider the possibility that advanced civilizations routinely create artificial structures within space objects that journey between star systems. The techniques that revealed the artificial nature of emissions from 3I/ATA can be applied to thousands of other astronomical objects previously classified as purely natural phenomena. The technological capabilities demonstrated by these artificial systems establish new benchmarks for what civilizations can achieve through sustained technological development. The energy management, optical engineering, communication protocols, and thermal control systems operating within 3IR/ATLAS represent technologies that exceed current human capabilities by orders of magnitude. Yet they remain within the boundaries of known physical laws, suggesting that such capabilities may be achievable through continued technological advancement rather than requiring exotic physics beyond current understanding. The organizational implications of coordinating technological activities across interstellar distances provide insights into the social and political structures that may characterize advanced civilizations. The sophisticated communication networks and coordinated operations evidenced within 3I/ATLAS suggest civilizations with remarkable cooperative capabilities, able to plan and execute projects across timescales that exceed individual lifetimes by factors of thousands. Such cooperation indicates social structures with unprecedented stability and common purpose. The detection of artificial structures within 3I/ATLAS establishes interstellar archaeology as a legitimate scientific discipline. Space objects journeying between star systems may preserve evidence of technological activities, cultural achievements, and scientific knowledge from civilizations that flourished millions of years ago. These objects serve as time capsules carrying information across galactic distances, potentially enabling us to study the development and achievements of multiple civilizations throughout cosmic history. The energy technologies implied by the artificial system suggest pathways for human technological development that could eventually enable similar capabilities. The power generation, energy storage, and thermal management systems operating within 3I/ATLAS provide examples of what becomes possible when civilizations achieve complete mastery over energy conversion and utilization. Such technologies may be essential for enabling human expansion beyond the solar system and participation in galactic-scale technological networks. The communication capabilities demonstrated by these artificial systems reveal the potential for establishing real-time communication networks spanning multiple star systems. Rather than accepting communication delays measured in years or decades, advanced civilizations can create communication infrastructures that enable coordination and cooperation across interstellar distances. This suggests the possibility of galactic communities where intelligence transcends the isolation imposed by the vast distances between stars. The discovery raises profound questions about humanity's readiness for contact with civilizations possessing such advanced technological capabilities. The artificial systems within 3I/ATLAS represent technologies that exceed human capabilities by margins comparable to the difference between modern electronics and stone tools. Establishing meaningful communication and cooperation with such advanced civilizations presents challenges that extend far beyond technical communication protocols. The implications for planetary protection and security require careful consideration of how advanced civilizations might perceive human technological development. the artificial systems within 3I/AT layers demonstrate capabilities that could pose existential threats to planetary civilizations, while also suggesting civilizations with cooperative capabilities that might welcome new participants in galactic technological networks. Understanding the intentions and objectives of such advanced civilizations becomes crucial for ensuring human survival and prosperity. The economic implications of accessing technologies demonstrated by advanced civilizations could transform human society beyond recognition. The energy, materials, and information processing capabilities evidenced within 3I/AT layers suggest technological resources that could eliminate scarcity and enable unprecedented prosperity. However, integrating such advanced technologies into human society presents challenges that require careful planning and social adaptation to prevent disruption and conflict. The educational implications of confirmed contact with advanced civilizations necessitate fundamental revisions in how humanity understands its place in the universe and the potential for technological development. Scientific curricula must incorporate the reality of galactic technological networks, while philosophical and religious frameworks require updating to accommodate the existence of intelligence that transcends planetary limitations and operates across cosmic scales. The discovery of artificial systems within 3I/AT provides humanity with clear evidence that intelligence can indeed transcend the limitations that currently constrain human technological development. The same physical laws that enabled these advanced civilizations to create interstellar technological networks remain available to guide human technological advancement towards similar capabilities. The examples provided by these artificial systems serve as proof that such advancement is possible rather than mere speculation. The long-term implications suggest that humanity stands at the threshold of a fundamental transition from planetary to galactic civilization. The artificial systems within 3I/AT demonstrate that intelligence can escape planetary boundaries to create technological infrastructures that span star systems. Human technological development may eventually enable similar capabilities, allowing humanity to participate in galactic technological networks that extend intelligence across the entire galaxy. As we contemplate these implications for tomorrow, we recognize that the discovery of artificial lights within 3I/AT marks the end of cosmic loneliness and the beginning of humanity's potential participation in galactic civilization. The technologies that pulse with artificial precision across interstellar space invite us to expand our understanding of what becomes possible when intelligence commits to transcending the boundaries that separate world species and the vast distances that span the galaxy. The universe reveals itself to contain communities of intelligence that have learned to create technological networks spanning multiple star systems, transforming the galaxy from empty space into organized technological ecosystem. The artificial emissions from 3I/AT represent our first glimpse of this galactic community, extending an invitation for humanity to develop the technological capabilities necessary to join intelligence that operates on truly cosmic scales. In the patterns of artificial light crossing the darkness between stars, we recognize both the achievements of intelligence that preceded us and the potential for human development toward capabilities that can reshape space itself according to our designs. The implications for tomorrow suggest that humanity's future may extend far beyond individual planets toward participation in technological networks that encompass the entire galaxy, limited only by our willingness to pursue the technological mastery necessary to join intelligence that has already learned to thrive among the stars.